Financial Modeling, Topic 7, Section 3. We're going to create an Excel stochastic portfolio model with multiple periods, changing asset allocations and contributions. We're not going to use the at-risk software. That's the next section. However, we're going to use macros to run our Monte Carlo simulation. So we'll go to our spreadsheet. The last section, we built the stochastic model, meaning there's only one possible deterministic single value that it comes to, and that is that $1.319 million. I'm going to use the same information, except for this time I'm going to use this column here, which is the standard deviations. Notice when we did the static portfolio, I did not use the standard deviations anywhere. So I'm going to have this formula here. My portfolio is going to start at $1. It's then going to grow at 7.28%. plus a random shock, my random z, norm S inverse ran, that's that random z variable that's normally distributed, times the standard deviation, plus my contribution. I'll copy that down, and now what you see is every time I hit F9, let's go look at this number right here. Every time I hit F9, that's a different lifetime based on the ups and downs and randomness of the market. So I hit F9, I wind up with $900,000. That's a worse than expected outcome. 1.08, worse than expected. 2 million, much better than expected. 1.3 million, about average. See, every time I hit F9, I get a series of 40 new random variables from age 25 to 65. And that generates the gyrations of the 40 years of the market. I then have my lookup, and based on the last gyration, my last gyration here, or iteration, is $1.1 million. There's the $1.1 million. And if I do get $1.1 million, that iteration, that random outcome, gives me a $60,000 annuity, wealth to income ratio 7.6, and replaces 41% of my income. And every time I hit F9, that's a different lifetime of savings. The next step I'd like to do is I would like to generate, say, 5,000 different lifetimes. I'll capture this number here, 5,000 times. I'll put it over here. Here's my 5,000 portfolios. Based on those 5,000 portfolios, I'll then take, say, the average of those. I'll take the 5% smallest and 5% largest and think about the risks of this portfolio strategy. Now to do that, I'm going to use a macro. The macro is right here. I'm going to use SimPort 5000 for I equal 1 to 5,000, next I, and it's going to loop and do these calculations, these two lines of code, 5,000 times. Cells 11, 13 equals 5,000 minus I. 11, 13, I'll go to the 11th row, 13th column. That's going to be right here. That's going to be M11. And then I want to start putting the iterations down here. So what I'm going to do is I'm going to specify cells 12 plus I, 13. In other words, when I is equal to 1, it's going to be in cells 13, 13 is equal whatever's in cells 5, 10. Cells 5, 10, we look over here, 5th row, 10th column is right here. So it's basically going to take this number right here and place it here, then here, then here, then here. Every time it does that, I get a brand new set of 40 randoms, those norm S inverse rands. I've attached that macro to this art object. There it is, SimPort 5000. And I'm going to run it. This is the countdowns from 5,000 to 1 or 0. These are my 5,000 outcomes. And by the way, I've given this column of 50 rows a range name of Sims. So if I Control Shift down, notice it has a name of Sims. So now I can go back and start thinking about the strategy and the distribution of outcomes. I'll first take an average of SIMs. So on average, I should get $1.32 million, which by the way, should give me about this value right here, right? $1.319 million. But that's not the point of doing a simulation. We knew what the expected value was going to be. The more interesting part is doing the small and large. So let's say equals small. The array is SIMs. And what I want to find is the 5% smallest. So I'll put 0.05 times 5,000. So the 5% smallest number in this column of 5,000 rows is $582,000. I'm going to copy that over here and change this to large. What is the largest? 5,000. Largest 5% of those numbers is $2.5 million. And then I'm just going to copy the retirement annuity, the real annuity, the wealth to income ratio, and the income replacement. Looks like I already have two of them in there. Let's copy these two. It's simply a formula. Paste, paste. And it's just going to replicate building that annuity at 3.5% for 30 years in retirement. And the present value of that, the real value of that today for 40 years later. And what that tells me is the average of the simulation is roughly the values of the deterministic static model. What's interesting is the 5% smallest and largest, in other words, the tails. The 5% worst case scenario is I wind up with only $500,000, which gives me a retirement annuity $31,000, and I only replace 21% of my income. The 5% largest is I wind up with $2.5 million, which gives me 95% replacement of my income. So this is a way of doing a simulation using a macro, using my random walk model, which assumes normal distributions. That's what that random normally distributed standard Z value is there. And I've simulated this portfolio over 40 years and thought about the risks of my savings rate and asset allocation strategy. So in this topic, we calculated or created an Excel stochastic portfolio model with multiple periods, changing asset allocations over time with contributions. In the next topic, we'll do the same thing using at risk.